So guys, in this video I have made some changes, so please do watch till the end, or if you have watched this video previously, so please just fast forward to the end and watch the changes I have made in that video, so that if you have an inquiry, just put me in the comment section. Okay, so that's all guys, thank you.
What's up guys, welcome to your next video on Cpusim. So in this video we'll be talking about microinstructions. So let's get started. So first of all, come to Cpusim and then open your machine. In my case this is first.cpu. Now go to modify and microinstructions. So now we'll be create these microinstructions in these categories. So let's start from the last. So set condition bit. In this category we have two microinstructions. One is halt, so we just name this. Now the next one is decode. So in decode we have only one microinstruction called decode IR. And the register is of course IR. In the next we have input output. So in this we have two microinstructions named AC INPR and out R from AC. So now by default we have integer, so we have to convert this to ASCII because ASCII is what we deal with. So input, alright, for this it's output. So now logical. So in logical we have three type of microinstructions and one is not. So AC and DR. So AC and DR will go into AC. In this we have E not going to E. So this is also a not type of instruction. Now source one is E and destination is of course E. AC source 2 is TR. So it's good to go now. And shift, in shift we have two microinstructions for arithmetic shift right and arithmetic shift left. So AC logical type of shifting, direction right in this case, left in the other, so distance is 1. And in the next we have increment. So in increment category we have 4 microinstructions. Oh sorry, it's 4. So one is increment AC. So INC AC, I will give it these short names. Increment AC, increment AR, increment DR, increment PC. So now PC DR AR. So we have carry out bit only for AC and we will not be dealing with any overflow bit, and this one is extra, so delete this. So in set type of microinstructions we have only one, and this is set AC to 0. So set AC to 0, start bit is 0, number of bit is 16 because we want the whole register to be set equal to 0. So 16, value is 0. And memory access, in memory access type of microinstructions we have 6 microinstructions, 3 for read and 3 for write functions. and first one is AR. So memory operand will go to AR, and in this memory operand goes to DR. So it's reading from memory, so memory operand will go to IR in this case. RAM data address is AR for all these, because AR is address register, so AR will be containing address for all of these instructions. So now data will go into AR, data will go into DR, data will go into IR. So the next are three: write, and write. So in this case, MAR AC, MAR DR means data from the DR goes to memory address AR. So data from PC and data from DR. So good to go now, and this is test, so we'll come back to later. And arithmetics first. So in arithmetic we have only one, and it's add type of instructions. So AC plus DR. Add AC, source 2 is DR, as you can see here, and destination is AC, carry out bit is carry out, of course. And now transfer R to R. So in this category we have almost 9 or 10 micro instructions. So first of all, AC15, that's is DR0. AC gets DR. So in all these instructions, what happen is data from one register goes to data register and another data register. So the next is carry out bit gets AC0, and in this carry out bit gets AC. It's the most precise set of micro instructions for this category, because we can make as many instructions we want, but we have the least possible number of instructions, which is optimum AR, and AR gets PC. So one more left here, and this is so I get it, this is DR0 gets E. So now source is E, source is DR, source is PC, source is AR, source is DR, source is AC, source is SC, source is IR, and source is DR in this case. So source bit is 0 0 0 0 0 15. No, it's not 15, it's 16 in this case, because and in this case DR00 all zeros, destination SC, and this case is DR. In this case it's SC, in this case SC, AR, A, SC, PC, AR. So this is PC and this is AR. So So start with number of bits 12. In all other cases it's, in this it's 16, in this it's 12, in this it's 12 also, and in all others it's 1. Let me check. I've covered all these. Yes. So now the last one, and these are test instructions. We'll be using them for testing conditions like if else in C++. So these are 7, I guess. Yes, these are 7. So first of all it is if AC0, sorry, AC complete is not equal to 0, then skip. So let's skip this. AC start 0, number of bits 16, and not equal. So we will be using this for SZA instruction, that is skip if AC is 0. So all these microinstructions will be used for machine instructions. So if AC 15 not equal to 0, then, so let's copy this, then AC start bit is 15, number of bits 1, comparison not equal, value 0, omission 1. So next is if AC 15 is not equal to 1, so this will be used for SPA and SNAs. So then AC and bit is 15, number of bit is 1, and comparison equal, not equal also in this case. So refer to this for these, and omission 1, and value is also 1 in this case. If D7 equal 1, then skip. So DR, and this is 13, oops, I mean this is IR because we are dealing with instruction register. So bits number 13, 14, 15 in our case will be checked for this condition, and equal, and value is 7. So if 111 comes, that is value in decimal is 7. So omission will take place for 3, and this is if DR not equal to 0, then skip, and register in this case is DR, and next it is A. So next is if A not equal to 0, then skip. So if the last one, I remember this, it's I equal to 0, then skip. So I is mode indexing bit, means which kind of addressing mode we are using. So this bit will gonna tell us that. So SA, no, IR. So 12 in this case, because you will see in future that will be giving the 12th bit in IR. So is 0, 1, 1, and 16 in this case, because we are checking a complete DR register. Not equal, not equal. So I guess we are good to go now. So let's check that we have missed or not anything. Transfer arithmetic branch test set. increment shift logical IO decode. So I guess we are good to go. So save your machine by clicking Control plus B. So it's saved now. Also make sure save machine here. So now close this, and guys, please subscribe my channel, like this channel, and hope you get this video right, and comment below so that I can know what my videos mean to you, or you get them right or wrong. So if I have made any mistake, just let me know in the comment section below. So guys, hope you get this. Thank you for watching this video. Subscribe, like and share this videos. I will be back with the next video on machine instructions or fetch and decode phase, I guess. So thank you guys for watching.
So guys, I have made this video again. So now these are all the microinstructions that are working correctly, 100% correct. And so please do match your microinstruction with these instructions, because I have made two mistakes in this video. So the destination bit of AC15 from TR0 should be 15, and the test instruction D7 equal 1 should have number of bits 3, and it is high because we are checking for 3 bits, 13, 14 and 15. And while making that video I forgot to change that 1 with 3 and the 0 with 15. So let it be, and please do subscribe and like my channel. So I have made the changes, and make sure you do the same. So thank you guys. If you have any doubts or any query regarding this video, please mail me or just comment down the comment section. Okay, so thank you guys.